Good afternoon, boys and girls. It is a Saturday afternoon and the weather is allowing. It is very beautiful and sunny on the outside. And I hope that you are really having a good Saturday as well. Thank you for joining me. And today, you will be pleased that we will be continuing again with electric circuits, and we will be focusing on more and more questions from previous examination papers. And you will see that the questions that I have chosen for you, they really encompass all aspects of this particular topic, and or rather most aspects of excuse me about that, of this particular topic. So if you are really able to answer these questions, then you will be able to distinct this section at the end of the year when you write your paper one. So I hope you are ready for me and you enjoyed your other lessons, which is technical maths and EGD and so on. So we continue with technical sciences. Right, let us look at the lesson outline for today. Quickly, we will revert back to what you are required to know as per the examination guidelines for this particular topic, electric circuits. And then in features of the topic, basically we will be learning electric circuits, but we will be using questions from previous examination papers in order to concretize our knowledge on this section of the work. And I will be giving you more and thorough tips on how to prepare this work for your examination at the end of the year, which is actually very near because you are starting this month actually. So let us shoot straight to it. Remember what you are required to know from grade 11. You must be able to state Ohm's law in words, and we state it as follows. The potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. And you know we state it like that, and this definition will be 2 marks or nothing. We won't be doing any part marking. And this is the trajectory that I really want you to follow in working with definitions. And we must know and establish relationship that exists between current as well as voltage, as well as resistance at constant temperature. So we must be able to explain what happens to the voltage if the current increases, rather what happens to the current if the voltage, or what we refer to as the potential difference, is increased and the resistance is kept constant, and so on. So we must be able to work with that. And then we must know the differences and state them between ohmic as well as non-ohmic conductors and give examples of each. And that is where we talk about ohmic conductors, which are those conductors that obey Ohm's law, or non-ohmic conductors, which are conductors that do not obey Ohm's law. And we also know the examples altogether. For example, for ohmic conductors, we know that pure metals like copper are ohmic. We know that the form of carbon that we call graphite is also ohmic. And then we have non-ohmic conductors. Those are, for examples, diodes, your transistors, your LEDs, your the filament that you get in light bulbs, etc. So those are examples of non-ohmic conductors. So you must know, and you must know the difference between them. And then we must be able to solve problems using this equation. The equation R is equal to V over I. For circuits where you have a series connection of resistors and a parallel connection of resistors, as well as a combination of resistors that are in series as well as in parallel in a single circuit. Again, we must be able to use series and parallel resistors in combination with Ohm's law. So basically, we must understand how does adding resistors in series or adding them in parallel affect the total resistance of the circuit, and how does it affect the total current of the circuit. For example, if the EMF is kept constant. Then another definition that we must be able to work with is the definition of the EMF. And we know the EMF is the potential difference across a cell when the circuit is open. That definition, my dear learners, is also going to be for 2 marks or nothing. Altogether, it is the potential difference across the cell when the circuit is open. And I also want you to always remember, my dear learners, that when we talk about the potential difference, we are talking about the voltage. Then we must be able again to define that term internal resistance. And we define it as the resistance inside the cell when current flows through it. No calculations are required. So know this. Remember, when we say no calculations are needed, it's not part of the definition. The definition ends there as the resistance inside the cell when current flows through it. Then we must be able to talk about power as well as energy. And when we talk about power and energy, remember, you must be able to define the term power. And here power is defined in terms of electrical energy. So it is the rate at which electrical energy is converted in an electric circuit. So remember, I said to you, we will stick to one definition for power. We don't have to define it in terms of electrical energy, because at some point, defining it in terms of electrical energy will not necessarily be correct. So we will simply define the term power as the rate at which work is done altogether. So it is the rate at which work is done. And then we must know the SI unit for power, and we know that power is measured in watts. And we know the symbol that we use for watts, it's a capital letter W. Right. And then we must know the practical unit of power, and we know the practical unit of power is kilowatt hour, kWh. And this is the one that we normally use, for example, when we buy electricity and we do the cost of electricity altogether. So we must know how to apply that practical unit of power. And then we must be able to perform calculations of power using the following equations. And those equations are: power is equal to W divided by delta T, Or we can use another equation, which is P is equal to VI, or we can use P is equal to I squared multiplied by R, or P is equal to V squared divided by R. And again, my dear learners, remember here, I'm really just trying to sum up the topic for you. You must know how to apply any of these formulas. And you must also be able to know what each variable on each equation means. So remember this W there, my dear learners, it refers to the heat. It refers to the heat, or it is referred to the energy, or it refers to the energy rather. Right, so know that the delta T, we know that one simply refers to the time. So this is the heat or the energy that is, and remember when you talk about heat, basically we are talking about energy altogether. So it's one thing. So this is the heat or the energy that is dissipated or that is produced. So any of the words can be used, the heat dissipated or the energy dissipated, or the heat produced or the energy produced altogether. So please ensure that you know that these ones, I know you know quite well that V represents the voltage, which is the potential difference. I represents the current. We know P is definitely power. And then on this equation, we can see power is equal to I squared multiplied by R. So current squared, it means I will have the value of current and I have to square it altogether, multiplied by the resistance. Or power is equal to V squared over R, where we know the V is the voltage, the potential difference, divided by R, which is the resistance. So it will depend what has been given to you, and you can use any of these four formulae in order to calculate the value of power, right? So we must also deduce that the kilowatt hour refers to the use of 1 kilowatt of electricity for a period of 1 hour. So this is what we talk about. Remember, a kilowatt hour is a practical unit of power. So be able to deal with that. It's kWh, and remember the W there is for watt, so it must be a capital letter W. Often what I see is learners would write K and they would write WH. This is totally incorrect. This is a watt, so it must be a capital letter, and this will give us kilowatt hour. And then we must be able again to calculate the cost of electricity usage given the power specifications. And you know, when we talk about the power specifications, we are basically talking about the power rating of the appliances used, as well as the duration. If the cost of 1 kilowatt hour are given, that means if you know the cost per kilowatt hour, cost of 1 kilowatt hour are given, remember it means this is the cost per kilowatt hour, right? Remember that, my dear learners. And then the heat produced by the resistor in a circuit is given by W is equal to I squared R multiplied by delta T. Remember, my dear learners, we have more equations of this W. which is the heat produced or dissipated. And you can use any of those. They are there on your formula sheet. It will just depend which one is having variables which you have values for altogether, right? So we shoot straight to questions. And here we have a nice question, and it really tries to test if you understand your basic knowledge of electric circuits. It reads as follows. In the circuit represented below, the battery has an EMF of 12 volts. So the EMF is 12 volts. And negligible internal resistance. Remember, we need to know the definition of both the EMF as well as the internal resistance. And we know when we talk about the EMF, we are talking about the potential difference across the cell when the circuit is open. In other words, it is that potential difference across the cell when this circuit is open, when there is no current flowing in the circuit. Secondly, the definition of internal resistance. And we know internal resistance, and we know that when the internal means inside. And that is why when we define the term internal resistance, we say it is the resistance inside the cell when current flows through it. So if I were asked those two definitions, then I would have had 4 marks altogether. There they are. Remember, EMF, we define it as the potential difference across a cell when the circuit is open, and that gives you 2 marks. And when we talk about internal resistance, it is the resistance inside the cell when current flows through it. And that is also going to be 2 marks altogether, right? So know that they didn't ask us that, but remember, my dear learners, and this is a tip that I really have shared with you before, and I will share it with you. Perhaps it's your first time tuning in. When you deal with these questions, when you are studying, remember, you are not going to get the same question or the same circuit as this one. Something similar, definitely, but not this one. So you must use this as a learning curve. For example, when you read the question and it says, in the circuit represented below, the battery has an EMF of 12 volts. You stop there and you ask yourself, oh, I'm also required to know the definition of EMF. And immediately at that time, you try and remember the definition, you write it down, and then you become able and say, oh, no, I'm able to define the term EMF. If you're not able, then you go back and check, but, oh, what is meant by EMF again? You write down, this is how you are supposed to be studying. And so on. So there we have the circuit, and I want us to really look at the circuit and interpret it. So 12 volts is definitely the EMF, and then the battery is connected correctly. The positive terminal of this cell is connected to the negative terminal of another cell. You can see there, they've actually shown you a line between the positive terminal of one cell and the negative terminal of another cell. It's simply the same thing. Sometimes we show it, sometimes we do not. Then we check, we track our current. I always told you, you start with your current and you track it from the battery. So if you track it from the battery, what you are going to observe is that it is the total current in the battery, and it picks up 12 volts. So each electron that is passing through the battery has 12 volts. So 12 volts, the electrons move freely. The conductor has negligible resistance, so we still have the 12 volts because we are not using any volts. We are not overcoming any internal, rather, any form of resistance. It goes through. The ammeter there, you can see this is still the total current. So it means this ammeter will measure all of the current that is moving in the circuit. How do you know that? Because from the battery there, there's only one pathway, all the current in one pathway, all the current in one pathway, all the current in one pathway. So the current will be able to move through this ammeter, and that ammeter will measure the total current. We also know that this ammeter has such a low resistance that we find it to be negligible altogether. And if it is negligible, it means the current flowing through the ammeter will not use any of the volts. Then we still have the total current, the total current, the total current still. And the electrons are still carrying that electrical energy of 12 volts because they have not come across any resistor. There has never been an opposition to the flow of current. So again, at that point, my dear learners, you will agree with me that I still have the total current. Are we together? Then the current divides. When the current divides, some of the current goes through this conductor and through the 6 ohm resistor up until it comes and the current meets up there. Are we together? Right. Then what we also need to do is to check that what happens to the current that flows through this conductor. So when it flows through this conductor, it goes down, it goes down, it goes down, moves through the 2 ohm resistor, and then there it will go up, and the current will meet up there again. So at that point, I will also have the total current because the current divided at this point and it met up at that point. Are we together? Right. So let me just leave our diagram looking a little bit neater. So we are agreeing that at that point will be the total current. Then from this point again, the total current goes, and as it goes through this conductor, then goes through the resistor again, and then it goes all the way up until it picks up another 12 volts. So if I were to connect voltmeters here, and let's say there we call it V2, and then this one, let's say we call it V3, and let us say there I add a voltmeter and we call it V1. Now, my dear learners, remember, we try to make this easy for you to understand in explaining it. What you need to know is that where there is a resistor, like here, because current will be flowing through this resistor, it will be experiencing an opposition to the flow of current. As a result, there must be volts that are used. So when current is flowing, there is no way that V2 can give you 0 volts, V3 can give you 0 volts, V1 can give you 0 volts because there are volts that are used to move inside this resistor, for the current to be able to penetrate through the resistor, for the current to oppose the flow of, for the current to overcome the resistance, for the current to overcome the opposition to the flow of current. So be able to work with that. Again, my dear learners, what we also know is that if I were to connect the voltmeters here, V2 must definitely be equal to V3. Why? Because these two resistors, they are not getting the total current. They get the current that has been divided. So because we know for a fact that resistors that are connected in parallel, they are potential, rather they are current dividers, and they are not potential dividers. It means they don't divide the potential. So the potential is going to be the same for V2 and V3. And this is because all of the electrons are coming with their voltage. And when they come with their voltage, those electrons that go through the 6 ohm resistor, they carry the same voltage as those that went through the 2 ohm resistor. Now, I gave you more tips, my dear learners, and I said, whatever we ask you, or most of the time when we ask you, and you see that this circuit has a combination of those resistors that are in parallel and this one that is in series, the best thing to do is always to start and work with this resistor that is in series altogether. What we certainly know is if you look at electrons, for example, coming from this side, going this side and this side, and they are carrying 12 volts, what you definitely know is that the electrons will not use up all of the 12 volts there. They can't use up all of the 12 volts there. Why? Because when they get to this point, they must still have some volts left to be used on the 4.5 ohm resistor. So whatever the reading is on V2 and V3, we know it must be less than 12 volts. You can't be using up all the volts because you must save some of the volts so that you can move through the 4.5 ohm resistor. Even if you look at it from this side, from the positive terminal of this cell, and you come this way, it's the total current, all of the total current moves through there. So there are volts that are going to be used, but it can't be all of the 12 volts. Why? Because there must be volts that are left so that you can overcome the 6 ohm resistor as well as the 2 ohm resistor. Now, with that analysis of the circuit, my dear learners, I can tell you that we will be able to answer any question that we are going to be asked now. We are required to calculate the resistance of the parallel combination. So to calculate resistance of the parallel combination, we'll say 1 over Rp, you know that it's 1 over R parallel, is going to be equal to 1 over R1 plus 1 over R2. And I told you that you actually get a mark for that regardless of whether we giving you a formula or not. It's simply to say you are showing that we are having 1 over a particular resistor plus 1 over a particular resistor. Now, when we get the value of Rp, my dear learners, we know the value of Rp is always going to be a value that is less than 2 for this circuit. Why? Because the value of Rp is always lower than the value of the lowest resistance there. So it's a value less than the lowest resistance there. So if the lowest resistance is 2 ohms, then it means Rp will be less than 2 ohms. Then we'll say 1 over Rp is equal to 1 over my R1. It's up to me. I can say it's 6 plus 1 over R2, I know it's 2, right? So I choose any. And then 1 over RP is going to give me 1 over 6 plus 1 over 2. Just want to work it out quickly for you. Is going to give me it will give me 4 over 6 altogether. So 4 over 6 is 1 over RP. So if I want RP, I will take the reciprocal. So the reciprocal will be RP over 1. So RP over 1 will then give me the reciprocal this side, which will also be 6 over 4. Because whatever I do on the left, I must also do on the right. So RP over 1 is RP. Then we say 6 and we divide it by 4. Then just on our calculator, 6 divided by 4, and RP gives us 1,5 ohms. This is most likely, definitely 3 marks altogether. So this is our answer to 5.1. Then let us calculate the reading on the ammeter. Now the reading on the ammeter, and this is now question 5.2. Now I can see that this ammeter measures the total current. So it means I will need the total resistance and I will need the total voltage. What I definitely have is definitely the total voltage, and I am aware that the total voltage, which is the EMF, or the total potential difference, which is the EMF, is giving me 12 volts. I want the total current. It means I must have the total resistance. And to get the total resistance, I'm going to say total resistance is made up of this resistor that is in series because it gets the total current. And it is also made up of the resistors that are in parallel. So it will be made up of parallel resistance, which is RP. Then R series is 4,5 ohms. And then R parallel, we calculated it there, and we know that it is 1,5. Then 4,5 plus 1,5 definitely gives us 6 ohms altogether. So now we know the total resistance of the circuit, and most definitely I know you will get a mark. Remember, my dear learners, we were not shown this calculation, so we have to show it. Then we say R is equal to, so we take this to a second set of equation where we know that R is equal to V over I. The total resistance of the circuit is 6. The total voltage is 12 over the current altogether. Then okay, absolutely no space there. Right. Let me just write it there for you. We then take it there and we say R is equal to a value of V divided by I. Then the total resistance of the circuit, we agree it's 6. The total voltage is 12 divided by current. Because I substituted the total resistance, the total voltage, then this is definitely the total current, which is what the ammeter is measuring. And according to my triangle, I'm sure you remember that one. We know that if you want R, you will take V and you will divide it by I altogether. So if you want I, you will take the value of V divided by R. So 12 divided by 6 is definitely 2 amperes altogether. So this is more likely 4 marks. Another tip is if you didn't show us how you got this 6, obviously then you would have lost a mark there. That is the first one. Secondly, if you substitute the wrong value there, we can't give you a mark for substitution because we do not know where that wrong value comes from. But if you got here, for example, 9 ohms and you put it there, you would actually get a mark for the formula, mark for substitution, but you will forfeit the final mark. So show all your calculations. And then we must calculate the current in the 2 ohm resistor. So we want to know how much current is flowing in the 2 ohm resistor. We want the current there. Now, my dear learners, can you see here? Because V2 and V3 are the same, meaning the potential difference is constant. Where the resistance is low, the current will be high. And where the resistance is high, the current will be low, provided that the potential difference is the same. Now, the 6 ohm resistor is 3 times higher than the 2 ohm resistor altogether. In other words, in the 6 ohm resistor, then the current will be 3 times less compared to the 2 ohm resistor. In your 2 ohm resistor, the current, rather the resistance is low, it's 3 times less compared to the 6 ohm resistor. In other words, the current will be 3 times more. So if I know the total resistance to be, rather the total current to be 2 amperes, when the current divides here, when the 2 amperes divides here, I know the current that goes in there must be 3 times less compared to this one, or the current that goes through the 2 ohm resistor must be 3 times compared to the one on the 6 ohm resistor. So how can I do that? Simply mathematically. It means the current that is flowing through the 2 ohm resistor will be 1,5 amperes, and the current that flows through the 6 ohm resistor will be 0,5 amperes. Now that is working logically, and you actually know the answer before you even calculate it. So you will still calculate it because they want you to calculate it. But then because you already know the answer, you will know if you don't get 0.5 there and 1.5 there, then you are wrong. Because 1.5 amperes is 3 times more than 0.5, or 0.5 is 3 times less 1.5. So to get that, my dear learners, remember, and I will just erase this because I don't want us to have a misinterpretation or think we have values when we actually don't. Right. What I told you to do is start working with the resistor that is in series. You know why? Because if you want the current here, you know the resistance. So you must get the voltage altogether. So for you to get the voltage across the 2 ohm resistor, you must know what is the voltage that was used there. And after you know how much was used there, you will know how much will be left for the 2 ohm resistor and the 6 ohm resistor. So you work out the voltage that was used here. Definitely, we said this resistor is in series because it receives the total current. So it means the current there is definitely 2 amperes. So for 5.3, it will begin here, where we say R is equal to V over I. Then The resistance at this point is 4,5. The voltage at this point is what I'm looking for, divided by the current, which is 2 amperes. If I want V, I can see V, I must take R and multiply by I. So I must take the 4,5 and multiply it by 2, and then this one will give me 9 volts. So I definitely know that I'm using 9 volts. So because we always start with the one that is in series, what we will then do is we just track our current from there. It has 12 volts, all of it has 12 volts, all of it has 12 volts. When it gets to this point, it actually has 12 volts. Goes through the resistor, uses some of the volts there, and we calculated that it uses 9. It means when it exits, it will be left with 3 volts. Because you had 12 volts, you use 9, so you are left with 3 volts altogether. All of the electrons now have 3 volts. 3 volts, those that go up will have 3 volts. And those that go down will also have 3 volts. Altogether, my dear learners. Right. And then we will say, okay, those that went up have 3 volts. Those that came here, they have 3 volts. Are we clear? And we say, okay, then, okay, after you are done with this one, let me just erase this so that it looks neater. After we have this, you will say, okay, then it means the voltage on the 2 ohm resistor will be the fact that I had 12 and I used 9. 12 minus 9, and that is going to give me 3 volts. Then all those that go there have 3 volts, all those that go there have 3 volts. So now I know the voltage there, I know the resistance there, and most certainly I can say R is equal to V over I. So on the 2 ohm resistor, I will put 2, and then for the voltage, I know I have 3, and I will divide by I. And then to get I know that I must be V divided by R, and I'm going to get 1,5 amperes. And you remember we had written it, ne? Yeah. So we had 1,5 amperes, and we were able to get it without even performing a calculation, but we won't give you a mark if you don't perform calculations, because we wanted you to perform calculations. So we come back to that matter where I told you that please always make sure that you start with the resistor that is in series. Are we clear? Right, it makes all of the work easier. Then we are required to calculate the power dissipated in the 6 ohm resistor. So this is 5.4. So we want to know what is the power that is dissipated in this resistor. So Elena could say, I know the value of resistance, it's 6 ohms. I know the value of V, it's 3. So I will say P is equal to V squared over R. So I want the power that is dissipated here. The V is 3. So this will be 3 squared divided by the resistance, which is 6. And 3 squared divided by 6 means that 3 squared will give me 9. And if I take 9 and I divide it by 6, I get exactly 1,5 watts. Another learner could have said, Menier, power is equal to V multiplied by I. I know the value of V there, it's 3. I know the value of I. Remember, if it was 2 amperes and 1,5 ampere goes there, the current there, it will be 2 minus the 1. It will be 2, 1.5 goes there. So if I take 2 and I minus 1.5, it means 0.5 will go there. So basically here I have 0.5 amperes. Then I is 0.5. So 3 multiplied by 0.5 will give me 1.5 watts. Remember, it's power. Then three marks. Or I could have said power is I squared multiplied by R. Then I know my current there is 0.5 and I'm going to square it. Remember, it's current squared, and I will multiply by the resistance there, which is 6. And then 0.5 squared gives me 0.25, which is a quarter. A quarter multiplied by 6, definitely a quarter of 6 is 1.5 watts. So any of these formulas is going to work for you. Altogether, great question, that one. Let us move to another circuit. Then they tell us in the circuit represented below, the battery has an EMF of 24 volts. We know what we mean by now. The battery's internal resistance is negligible and the resistance of resistor X is unknown. So we don't know the value of the resistance there. Then they tell us to state Ohm's law in words. We can do that. We know the potential difference across the conductor is directly proportional to the current in the conductor at constant temperature. And that definitely is going to give us 2 marks altogether. The potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. Then they tell us when the switch S is open. So now we are dealing with the switch being open. Ammeter A has a reading of 1.5 amperes. Now, some of the learners would be surprised what we mean when we say ammeter A has a reading of 1.5 amperes when a switch is open, because we sometimes just think when the switch is open, automatically there is no current that is flowing. And I remember in our very first lesson, I explained it thoroughly to you, and I said, it depends where the switch is located. If the switch was located there, somewhere here, right? Then this switch is controlling the total current, because from there to there is the total current, or from this all the way to there is the total current. So it cuts all of the current. But look at switch S there. Switch S is connected on this pathway where you have resistor X. And this is not the total current that is in the circuit, because the total current is actually there at that point. And then the current divides. And the current meets up here again. And there I have the total current. So this switch, if it is open, it means only this lane, only this pathway is not working. So the current will come this way, 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 but then it would go that way altogether. This lane will not be working anymore. Can't be working. Why? Because the switch is open. There is no current that can flow through there. So when we track our current, it goes from the battery all the way. It goes through light bulb, which is L. Remember, that's a symbol for a light bulb. It goes through there, it goes through there, through there, through there, all the way. So definitely there, that lamp, the total current moves through it because it's the total current from the battery, still the total current. Ammeter, still, I will have the total current altogether. Why will I have the total current? Because most definitely, my dear learners, we don't have current dividing at this point. Remember, the current will meet up there and it will still be the total current that is in the circuit. Are we together? So there we have the total current because the ammeter anyway, it is always connected in series at that particular point. Are we clear? Right. Then we say, okay, this lane, it means it's not working, but this lane is still properly working. This connection is definitely working, and that is why the reading is giving me 1,5 amperes. Then we are asked to calculate the potential difference across the 4 ohm resistor. It must be across the 4 ohm resistor. So I want to know what is the potential difference there altogether across the 4 ohm resistor. Now, if I know, right, that the current is 1,5 amperes, do you agree with me that because this lane, this pathway is not working, this is the total current, the total current, the total current, the total current, the total current. No current goes there, so it's the total current there, the total current. So in this case, it means I have 1,5 amperes that is moving. So to get the potential difference there, meaning the voltage used there, I will say, and this is question 2.2. For question 2.2, I will say R is equal to V divided by I. The resistance there is 4 ohms. The voltage is what I'm looking for. And the current is 1,5. Then to get the value of V, this is definitely going to give me 6 volts. This is definitely going to give me 6 volts, and I will have 3 marks there altogether. So 6 volts means that is the number of volts that are used to move 1,5 amperes of current through a 4 ohm resistor. Then we must calculate the resistance of lamp L. Remember, a lamp is actually a light bulb and it has a resistance altogether because of that filament that is in the lamp, the filament that is in the bulb. So I want the resistance of lamp L. Now, my dear learners, do you agree with me that if I know that there I used up 6 volts, remember now, this resistor is getting the total current. This resistor is getting the total current. So these two resistors are connected in series altogether. Now, if they're connected in series, we know that these are the only resistors. A resistor there, current flows, a resistor there, no resistance, no resistance, no resistance. It means this 24 volts, it must be used to overcome the resistance through the lamp and to overcome the resistance through the 4 ohm. In other words, if I used 6 volts there, definitely it means for lamp L, I have used 18 volts. How do I know that? The total voltage, I have 24. So if I use up 18 there, then I'll be left with 6, and I use up the 6 volts there, and I don't have to use it anywhere else. So for 2.3, we'll start by saying the voltage of the lamp is going to be 24 minus the volts that I used there, which is 6, and therefore the V of the lamp is definitely 18 volts altogether, and that carries a mark because we didn't show you the calculations. So now there I know I used 18 volts. I know the total current that is moving there, which is the total current. I know it is 1,5 amperes. So to get the resistance there, I will then go further and say R is equal to V divided by I. The resistance, this is what I'm looking for. The voltage used is definitely 18, and the current is 1,5. Then I'm going to say 18 divided by 1,5, and I'm going to see that the resistance there is definitely 12 ohms altogether. Let's correct that. I wrote amperes and I'm saying ohms. So this is definitely going to be 12 ohms. This is most likely 4 marks altogether. And there are quite a number of ways that I could have done it. I could have calculated the total resistance that is in the circuit. After I calculate the total resistance in the circuit, then I will take the total resistance and I will subtract the resistance of the 4 ohm. Then that would have given me the resistance of the lamp. So that would still have worked. Then we are being told when switch S is closed. Now we close the switch. They tell us that ammeter A has a reading of 1,6 amperes. What do I see here? I can see that after I closed the switch, the reading on the ammeter increased. So after I closed the switch, the total current of the circuit increased. So if the total current of the circuit increased, I can take note that the EMF was never changed. So the EMF was kept constant because we didn't increase the number of batteries or decrease them. But I see that the current increased. So when the EMF is kept constant and the current increases, it means the total resistance of the circuit decreased altogether. So I'm going to remove a lot of things here because this was only true when the switch was open. So now we are dealing with a switch that is closed. Altogether, the switch is closed. Now, if the switch is closed, the fact of the matter is I still know at this point I'm getting the total current, which we were told is 1,6 amperes. There, the total current is 1,6 amperes. Now, what we realize here, my dear learners, is that immediately when I close the switch here, then there is nothing wrong with that pathway. So that pathway where you have resistor X connected is most certainly working. Altogether, it is most certainly working. And if it is working, my dear learners, it means this circuit is still correct and the pathway is working. Now, when this pathway works, okay, that point I still know it is the total current. There I still know it is the total current. Now, my dear learners, what we also then realize here is that by making this switch work, this switch was actually controlling that lane only, not the total current. That is why the circuit was still working even if it was open. Can you see that? It then tells me that I have added a resistor in parallel. And I know that by adding resistors in parallel in a circuit, the total resistance of the circuit is going to decrease. Remember that when you start to add resistors in parallel in a circuit and the EMF is kept constant, then the total resistance of the circuit is definitely going to decrease. Why? Because you are providing an alternative path for the current. So the current now has more path, more routes that can be followed. So it means the total resistance is being decreased. Altogether, the opposition to the flow of current decreases, and that is why the current increased and the EMF remained the same. But you will recall that if I added a resistor in series, then the total resistance of the circuit would have increased. But for this case, making the switch to be closed makes X to work. In other words, I have added the resistor in parallel, so the total resistance of the circuit is going to decrease, and that is why the current increased. And this is how you learn, my dear learners. Then we are asked to calculate the effective resistance of the circuit. And this is something that you should familiarize yourself with, because sometimes we can say the total resistance, the effective resistance, the equivalent resistance, we can do whatever. The fact of the matter is we specify, we are saying of the circuit. So it doesn't matter which word I use. If I say of the circuit, it means I'm interested in the resistance of the entire circuit. I haven't singled out parallel. I haven't singled out resistance in series. I said resistance, effective resistance of the circuit. In other words, I'm talking about the entire circuit. So if I want the total resistance of the circuit, it's absolutely not a problem. The EMF is still 24, which is the total voltage. The total current, it's still 1,6 amperes. So if I want the total resistance, which is then question 2.4, then the total resistance, which is of the circuit, which is the effective resistance of the circuit, will be given by R is equal to V over I. So I want the resistance of the entire circuit. I will use the total voltage of the circuit, which is 24, and I will divide by the total current of the circuit, which is 1,6. And this is going to give me a total resistance of, definitely it's giving me 15 ohms. So the total resistance of the circuit is definitely 15 ohms. We get all the marks there. Very easy one. Then we are asked to calculate the effective resistance of the parallel combination of resistors. So you see, we still want effective resistance, but we specified which effective resistance. And this time not like 2.4. In 2.4, we wanted that of the circuit. Now we want the effective resistance, but we have specified of the parallel combination of resistors. So we basically are looking for R parallel. How do we do that? Remember, my dear learners, originally in 2.3, remember I had calculated the resistance of this lamp to be 12 ohms. So I don't need to recalculate the resistance of the lamp. It's a value that is there for that lamp. It's 12 ohms. So if I want R parallel, I know that, and I want to show you this first and see if it will work for us. Okay, I want R parallel. Most of us would have started there and said 1 over RP, it's 1 over R1 plus 1 over R2. And what is our aim? Our aim is to get that RP. Then we say 1 over RP will be equal to 1 over, this is X, plus 1 over 4. And the learner says, okay, this one will be a problem because I don't know the value of X. Then you don't give up and leave it out. You try other methods altogether. So I did this intentionally so that I can show you that, okay, most of us would have really followed that route, but now we see that it doesn't work. So how can we get R parallel into a formula? You can actually do this. You can actually say, okay, the total resistance of the circuit is actually given by the resistance of the resistors in series plus the resistance of the resistors in parallel, because I have this lamp in series, I have this in parallel. So if I wanted the total resistance, I would have added the resistance in series plus the resistance in parallel. Then the total resistance, my dear learners, is definitely 15 ohms, isn't it? Yeah, we calculated it. And the resistance in series is 12. And this will be plus RP. Then if I want RP, I will take the 12 to the left. So it will become negative. So it will be 15 minus 12. And this would give me RP to be 3 ohms altogether. So now I know the value of RP. Can you see that? So you need to check what you have. Then we go to 2.6. So now we are going to answer question 2.6. In 2.6, we are being asked to calculate the resistance of resistor X. So we want to know what is the value of that resistance. The resistor is called X. So we want the resistance of that resistor, which is X. And that is where we start by saying, okay, what do we say there? We will say this resistor X, it's actually a resistor that is connected in parallel altogether. Now, my dear learners, there are quite a number of ways of doing this. Ne? I could actually just say the easiest one. To get this into a formula, that value of X, I can say because it's R parallel combination, I try what I'm used to. 1 over RP is equal to 1 over R1 plus 1 over R2. And then we check, we say, okay, 1 over, I have the value of RP, remember, it's 3. So it's 1 over 3 is going to give me 1 over R1, resistor 1, we take it to be X, plus 1 over R2, and R2 is given as 4. There it is. Then 1 over 3 minus, remember I take the 1 over 4 this side, so 1 over 3 minus 1 over 4 is going to be equal to 1 over X. Then we go to our calculator, we try and find out the value of 1 over 3 minus 1 over 4. So this is going to give me mathematically, that would then be right, it would then give me 1 over 12. And that will be equal to 1 over X altogether. And then I don't want 1 over X, I want X. So I will take the reciprocal. So it will be X over 1. And X over 1 will give me 12 divided by 1 altogether. Then X over 1 gives me X, and 12 over 1 gives me 12. And because it is resistance, then it will be measured in ohms. In other words, the value of resistance there, my dear learners, is definitely 2 ohms. A mark there, a mark there, and a mark there for the final answer with the correct unit. Right. Then we move to the last question of the day. From previous examination papers, and it reads as follows. The circuit diagram shows 3 resistors connected to a battery with negligible internal resistance. 2 resistors of 6 ohm and 10 ohm are connected in series. So they are connected in series to each other. 6 and 10, they are connected in series only for this pathway. Okay, this combination is connected in parallel to a 4 ohm resistor, which is functioning at the power rating of 36 watts. Now, what are they telling us there? Or rather, let us check what is happening. There, I have a good connection, positive terminal of this cell to the negative terminal of that one. Then it's the total current, it is the total current, it is the total current, it is the total current. At this point, remember, excuse me about that. This is the total current, so the current divides. So some of the current will go in that 4 ohm resistor, some of the current will go down and it will go through the 6 ohm resistor and the 10 ohm resistor. So we must understand this, my dear learners. This pathway is connected in parallel to this pathway. Furthermore, the current that flows through there is not the total current. And the current that flows through there is not the total current, but the current will go, it will go there, and the current will also go through there. So from that point, I also have what? The total current. So at this point, I have the total current. So these two, although they are in series, they are just in series to each other. But this entire combination is in parallel to that one. So this line is parallel to that one. altogether. Right. Then we are required to define power in watts, and I told you we'll stick to one definition of power. We say it is the rate at which work is done. I will not write it down for you. We know this by now. The rate at which work is done. Number two, we are required to state Ohm's law in words. We must state Ohm's law in words. And we know it by now. The potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. Altogether, right? So that will give us 2 marks. We know this definition, my dear learners, we know it. The potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. So this gives you 2 marks or nothing. Then we are required to calculate the following: the current in the ammeter. So we want the current in the ammeter. So this is 9.3.1. So obviously this ammeter is measuring only the current that is flowing through this lane altogether. So if the resistance is 4 ohms and this resistor has a power rating of 36 watts, then we can check the current that flows through it altogether. Then there are quite a number of formulas. You see, I have power and I have resistance and I want current. So the formula that will be relevant for me is the formula that says power is equal to I squared multiplied by R. We talked about this. It's there in your formula sheet under electric circuits. So the power is 36 watts. So I will have 36 there for P. The current is what I'm looking for. So it's I squared, and the resistance there is 4 ohms. Then current squared will be, if I want to remove the 4, I will divide by 4 on both sides. So 36 divided by 4 is most certainly going to give me, I think it's a 9. Okay, I don't think it's a 9. It's definitely a 9. Then I'm not looking for I squared, I'm looking for I. So I must take the square root of I squared, which is I. Then what I did on the right, I must do on the left. So I took the square root of I squared, which is then I. Then the square root of 9 is definitely a 3. So I is definitely going to be 3 amperes. 1, 2, most definitely is 3 marks. Yes. Right, I will get 3 marks. So there are a lot of formulas for power. The one that is relevant is the one where I'll have the power, I'll have the resistance, then I can calculate the current. Then we want the potential difference across the 4 ohm resistor. So we know the current that is flowing through there. So we want to get the potential difference across this resistor. We are looking for the value of V. Such a simple one to do as well, my dear learners. We know that power can also be given by V squared over R. So this is question 9.3.2. And I know my power, it's 36. I know my V is what I'm looking for, so it will be V squared divided by the resistance there, it's 4. So V squared is going to be given by 36 times 4. So 36 times 4, if you calculate it, it gives you 144. Remember, you don't want V squared, you want V. So To get this to V, you'll take the square root of V squared. After you take the square root of V squared on the left, rather on the right, you will get V. And because you took the square root on the right, you must take the square root on the left. And the square root of 144 is definitely 12. So this is going to give me 12 volts. And this is most probably 3 marks. Are we together? Right. So that's how you would have calculated it. Something perhaps that you could have done is to try a different formula where this is still 9.3.2 as well, where you just say P is equal to VI. So you know the power, it's 36, is equal to V, it's what you are looking for. The current that is flowing through there, remember, is that 3 amperes current, which we calculated there. So it will be times 3. So if you want V, it will be 36 divided by 3. You will still get 12 volts. So that still gives you the same answer. And it is 3 marks. Right. Then we are required to calculate the current in the 10 ohm resistor. Now, if I want the current in the 10 ohm resistor, then I need to go and check. And I say, okay, what I know here is that if I were to connect a voltmeter there, then this voltmeter would have given me 12 volts altogether. It most certainly would have given me 12 volts. Now, if it would have given me 12 volts, why can I conclude that? Because if I connect a voltmeter there, I definitely know that it will give me 12 volts altogether. I calculated it. So because these are not potential dividers, they only divide the current. All the electrons that went through there, they had 12 volts. So all those that will go through there, they will have 12 volts. So when they flow, when they come in having 12 volts. Remember, they have the 12 volts, most definitely 12 volts. They go through. 12 volts, they use up all of the 12 volts because after this, there is no resistance. So those that went into this resistor, they will go with 12 volts. Those that go down, they will go with 12 volts. So before they go through the resistor, they have 12 volts. After they exit this last resistor, they will have 0 volts. So if I connected the voltmeter there, I will definitely get 12 volts altogether. But if I connected it only on the 6 ohm resistor, I wouldn't get 12. I wouldn't get 12 there. Now, I know the total voltage there to be 12 volts. So if I just look at this line only, I can say, okay, the total voltage to be used in this line is 12 volts. This is VT. And then the total resistance in this one, in this line only, is going to give me 16 ohms because this line only, they are connected in series. So this pathway, the resistance, I'm going to add the resistors. It will be 10 plus 6. It will give me 16 ohms. Altogether, my dear learners. So this is only applicable to this pathway. So now, if I know this, then what I will do is I can calculate the total current flowing only in this lane altogether. So the current that is flowing in this lane, I would have said, okay, now I'm doing 9.3.3. For that lane only, R is V over I. The total resistance of this pathway is 16, and the total voltage of this pathway is 12. So the total resistance, we said it's 16. The total voltage of that pathway is 12 divided by I. And you will remember our triangle where R is V over I. So if I want the value of I will take V, I will divide by R. So it means I will take the value of 12 divided by 16. So if we get 12 divided by 16, I find that the current flowing in this lane is 0.75 amperes. So in this lane, my dear learners, I saw that 12 volts came through and it worked for a total resistance of 16 ohms. So the total current flowing in this lane only this is for the pathways, not for the whole circuit. This is for the pathway. Then it would have given me the total current of this pathway to be 0.75 amperes. Okay. Right. Now, if it's 0.75 amperes, then what do I know? It means the current that will flow in this lane, there, it will be 0.75 amperes. And all of it will pass through. Even there, it will be 0.75 amperes. Now remember, this was only one resistor on this pathway. That is why it used up all of the 12 volts. But when they come through on this lane and they have the 12 volts, then the 12 volts can't be used on only that resistor or only on that resistor. It must be used to overcome these two resistors. So the 12 must be shared between the 6 ohm and the 10 ohm. It must be divided between the 6 ohm resistor and the 10 ohm resistor because they are connected in series. So to get this one, I know the resistance, I know the current. Then I will say, I will just take this calculation further and I will just say R is V over I. And then the resistance there is 10 ohms. The voltage, in fact, in my head now, I'm thinking we want the voltage across the 10 ohm resistor. We actually wanted the current in the 10 ohm resistor. And basically our calculation just ends there altogether. Our calculation just ends there because you knew the total voltage there, you knew the total resistance in this lane, so you calculated the total current in this pathway. So the total current is in this pathway is the current that passes there and the current that passes there. And that is why it must actually end with 0.75 amperes. So what I was taking it down to is we can calculate the voltage there and the voltage there, but together I know the voltage that I get there and the one that I get there is definitely going to give me 12 volts. And it's an easy one. Then we want the current in the battery. My dear learners, pretty much obvious. If I want the current in the battery, remember all of the current has to move inside the battery. Why must it move inside the battery? Because the current must continuously pick up the electrical energy from the battery, the EMF. So I calculated that in this lane, I had 3 amperes. I calculated that in this lane, I'm having the total current of 0.75 amperes. So the total current will be given by I total is going to be the current that flows in this lane, which is 3 amperes, plus the current that is flowing in this lane. Remember, some of the current went there, some of the current came through there. So the total current divided into 3 and 0.75. So the total current will be 3 amperes plus the current that went through there, which is 0.75. Right. Remember now, when we perform our calculations, we don't include the units. So 3 plus 0.75 is definitely going to give me 3.75 amperes. And that is why this is just 1 mark. So you will get a mark there altogether. Right. And that one is 4 marks. Are we clear? So my dear learners, be able to work with these type of questions and interpret, and you will see that it becomes very easy. So remember, my dear learners, electric circuits, they count plus minus 15 marks, and that is for paper 1. And you can really do well in this section. I've really tried to make it easy for you, but I want you to appreciate the fact that you have to do some digging, you have to do some groundwork, you have to interpret, and you must be able to see if the answer is not making scientific sense and when it is making scientific sense. So please work on everything, go through your examination guidelines, take the formula as it is from the formula sheet. Remember, we need a formula, we need substitution, we want an answer, and we also want units altogether. Always work with that. And don't just put in values, do the groundwork, my dear learners, and that is why we are examining you. So thank you very much for tuning in. You can send me more questions to stemdigitalschool@africateengeeks.co.za, and I will see you on Monday between 6 and 7 o'clock in the evening when we start a different topic in technical sciences. I definitely hope that you are more learned in this section of the work and that you will do well. Thank you so much for tuning in, and I will see you tomorrow, rather on Monday. Goodbye.